Okay, so now we will talk about the Simpsons quadrature formula. So in the previous lecture, we talked about the trapezoidal formula and also its geometric interpretation. So actually the Simpsons formula is based on the idea that actually we can take one more function evaluation. So we were talking about an interval like a and b, and we have evaluated our function f of x at these points in the trapezoidal rule by connecting the lines basically that approximated the f of x with these linear lines. But now actually we want to reverse engineer and we want to actually obtain a quadrature formula that is exact for polynomials of degree less than or equal to 2. And in order to do that, we need to approximate our original f of x with a polynomial of degree 2. Okay, and if we write the equation of a polynomial with degree 2, how many coefficients do we have? So we have actually 3 coefficients, right, for a polynomial of degree 2. So here what we will do is basically we will write down these weights. So we will have actually 3 unknowns, and we will require that this approximation on the right hand side is exact for polynomials of at least degree 2. And actually at the end of the derivation we can also see that actually it's also exact for polynomials of degree 3, which is going to be an extra outcome of this method. So let's start how we can derive this Simpson's rule. So first you take the constant term, because if your f of x is a constant function which can be just equal to 1, right? So actually this can be seen as 1 times dx. So if you are trying to integrate this, and if your f of x equals to 1, then what's going to be the value of f of 0, f of 0.1, and f of 1? So the values are all going to be equal to 1, so we can get basically w0 plus w1 plus w2. So notice that the right hand side is what we get from the quadrature, and which is going to be actually a second order approximation polynomial. Therefore it will have 3 terms, 3 weights. So our goal here is to obtain what is these weights exactly. And if we can find the values of these weights, then we get ourselves a quadrature formula, because we are evaluating our function at 3 points. Okay, so additional to the trapezoidal rule, basically the Simpsons rule will also consider this midpoint, which is a plus b divided by 2. So the Simpsons rule takes one step ahead of the trapezoidal rule, because in the trapezoidal rule, remember, we have the lines, and from 2 points you have only 2 unknowns, and you can solve it using these 2 points. That gives you the trapezoidal rule. But in the Simpsons rule, notice that we want our formula to be exact for polynomials of less than or equal to 2 as the order. So that means we need one more point and one more function evaluation at this midpoint. So therefore we have these 3 terms. So basically now notice that if your f of x is just equal to 1, basically you can get one equation in terms of w0, w1, and w2. And again, our method is supposed to be exact for polynomials of degree 1 as well. So if you have f of x equal to x, right, then what's going to be the right hand side? So f of 0 is going to be 0, so we don't have any w0, and then this is going to be 1/2 times w1, and you have 1 times w2. So you get again right hand side from the approximation formula here, which is in terms of the unknowns currently. And finally, for the second order term, if your f of x equals to x squared, again we expect it to be exact. So being exact means the exact value of the integral must match with the approximation. So again, you can plug in these values. F of 0 is again 0, and you have 1/2 squared, this is 1/4, and you have 1 times W2. And obviously we can integrate these left hand sides exactly, so this gives you 1, 1/2, and 1 over 3. So now what do we have here is basically 3 unknowns, which are the weights that we are trying to find, and we have 3 equations. So this can be solved. And if we solve this equation system of these linear equations, basically we get the weights for the Simpson's quadrature method. So this was written for simplicity for the interval between 0 and 1, but actually you can easily generalize this to a to b. Okay, and also notice that our choice of these functions are actually as long as this is a, let's say, a constant, it doesn't matter, you choose this constant equals to 1 or 2. And similarly, as long as your second equation here, f of x is a line, you can choose another line, for example, f of x equals to x minus 1. Doesn't matter. This doesn't matter because those right hand side will also change accordingly. Okay, so this is just in parentheses. And also similarly, this is just a generic, let's say, second order polynomial here, and you can also consider something different, doesn't matter, because again, everything on the right hand side will change accordingly, and it will not affect your result for W. Okay, so basically, as we can see here, we generalized what we have as the Simpson's quadrature formula for the interval a to b. And you can notice that basically we have this is the length of the interval, b minus a, and we are doing some function evaluations at the left end point, right end point, and the midpoint. So the midpoint has this coefficient 4 over 6, and f of a has coefficient 1 over 6 and 1 over 6. So this is already the quadrature formula that we obtained by solving our linear system of equations. And interestingly, we required from the beginning our method to be exact for polynomials of degree less than or equal to 2. But indeed, it turns out that the Simpson's quadrature formula is also exact for polynomials of degree 3, which is something that we didn't require from the beginning. And we can easily verify that. So if we have a polynomial of degree 3, like f of x, in this case x cubed, and what's gonna be the exact result, we can directly integrate this. So the integral, so this is x to the 4 divided by 4, and you evaluate this, basically you get b to the 4 minus a to the 4 divided by 4. And on the other hand, you can also evaluate your formula, and basically you can evaluate this quadrature formula here, and this is what you get from the quadrature formula. But if you do the algebra here, basically this is exactly the same as the exact solution of this integral. So this shows that Simpson's rule is also exact for polynomials of degree 3.